This is Unit 7, Day 7 notes, and they start on page 19 of your packet. And we are still talking about finding particular solutions of first-order differential equations. So first-order differential equation, again, are those differential equations that have a first derivative in them and nothing other than that in terms of derivatives. We're still talking about particular solutions. We started this in the last class. And in the last class, we had some polynomial examples and some trig examples. And in this class, we're going to be really focusing on logarithmic and exponential solutions. And so these are more complex, typically because people aren't as strong with their logarithmic and their exponential derivative rules and properties and stuff. So this is it's going to be a more advanced day. Okay, so the first thing we need to do is, and you can just squeeze these at the top of your page in your notes. So that would be like the top of page 19 or something like that, right above the first example. We need to know these. Okay, this is like, you know, these values and these properties down here. These are as important as the unit circle, and the unit circle is pretty important. So these are things that you know, I almost never say this except for on this day at this time. But you know, when we talk about the unit circle and we talk about these properties, if you don't know these things, you should feel a little embarrassed. Okay, and I almost never say that except for in this instance. These are things that you gotta know. You gotta be able to work through, get them down, know them immediately, so that you can just spit them out really super fast. Because otherwise they'll trip you up time and time again. So you get this in the unit circle, maybe go through that unit circle Blackboard summative that we had earlier again. Maybe I should reassign that this semester, but that's a whole other subject. But you got to know these, super, super important. Okay, let's start with the natural log of 0. So natural log of 0 doesn't exist. So this is where you need to know what the natural log graph looks like, right? The natural log graph, if you don't know what it looks like, go back into unit, I think it was unit 5, where on the back of your schedule, I gave you all of those functions and their shapes. Find the natural log, know that shape. Okay, there's an asymptote on the y-axis, so we never reach a 0 value. That's why this number here, the 0 is, always has to be positive, because there's no part of the graph that's in quadrants 2 and 3, where the x is negative. Okay, natural log of 1, that's 0. This is the x-intercept. Okay, natural log of e, so if we go over e from the origin, okay, we're going to be up 1. So you got to know those so that they come out that fast. Okay, let's talk about exponential values. Okay, so again, go back to that sheet of graphs from unit 5 on the back of your schedule. Find e to the x, find that, and know what that shape looks like, right? It's the inverse of the natural log. Remember, we talked about inverses being reflections over the line y equals x, because inverses swap the x's and the y's. So where the natural log has an asymptote along the y-axis, exponentials have an asymptote along the x-axis because they're inverses. Okay, so e to the 0. When x is equal to 0, this is the y-intercept. Oh, well, I guess I didn't get to that point. Okay, let's talk about the differences. When we have the natural log of a number minus the natural log of a number, we can write that as a quotient. So this is also super important, especially on multiple choice, because you'll never see an answer form in this way. You'll see an answer form this way. Okay, now let's talk about the exponentials. Y-intercept, so e to the 0 is 1. Anything to the 0 is 1. So all exponentials, as long as they just have an x up here, they will go through that same y-intercept. E to the 1, when x is equal to 1, the function is e, right? That's 2.7 and a little bit more. E to the negative 1, that's 1 over e. Okay, that's super important to recognize that as a fraction. Okay, e to the natural log of 2. This is an identity. E to the natural log of 2 allows us to bring this down in front and call it 2, because e to the natural log by definition is an identity. So this is just the value that you see here. So e to the natural log of y then is just y. And this is important for solving differential equations, because the differential equations we'll talk about today are going to be equations where the antiderivatives are natural logs, and we're going to have to solve for y. And that's a way of solving for y. And then recognizing that e to the x plus y, if we have a sum or a difference up here, that we can rewrite it with its own base, e to the x times e to the y. Now this is a product. Now we can separate it, which is important for separable differential equations. So that's why those properties are super important for differential equations. So you might want to pause the video if you're doing more listening than writing. Write these down at the top of your page 19. Make sure you know how to do. Make sure you know these values. Make sure you know these properties for exponentials and properties for natural logs. Super important. Just a quick side note, log logs, log base 10, we don't work with in calculus, so you won't see logs. You just see those in forests. Okay, so let's look at the first example. I called it example, I don't know why I called it example 4. I might have my numbering might be off here. It probably should be example 5, because we had 4 examples in the previous class. Anyway, okay, so if it says find the particular solution y equals f of x to the given differential equation with an initial condition f of 3 equals 1. So as you can see, compared to the previous class, the questions aren't any different, okay? But these solutions are going to involve natural logs. Okay, so if we look at this, we know the first step here is to multiply by dx, right? That's always our first step. Those cancel on the left. So, and then notice I'm trying to do this all in one step here. I got to multiply by this. So when we look at this, this is the product. It's a product of 2 minus y, the numerator, times 1 over x, the denominator. Okay, that's our product that we're separating. So the 2 has got to come with the y. Those are a pair. You can't just add y to both sides, because adding y to both sides is not a multiply divide process. So we have to multiply by 2, divide by 2 minus y, or multiply by 1 over. So they're going to cancel on the right, and we're going to have 1 over 2 minus y on the left. So looking at this, I know it's messy. There's a bunch of stuff crossed out, but we have 1 over 2 minus y dy on the left equals 1 over x dx on the right. So we have that. Okay. So you know that whenever you have 1 over x, when we do antiderivatives, it's going to be natural log of the absolute value of x. So this, because this is just a plain old y, there's no power to a 2 or a 3 or whatever, we know this is going to be a natural log as well. So we have natural log, natural log. That's the scenario we have here. So this one, now we got to look for the reversal of the chain rule, right? This one, its derivative is -1. So this is tricky, but you'll see this a lot. So this is the natural log of 2 minus y divided by -1, right? We're dividing out the derivative of this u sub here. Remember, the u sub and reversing the chain rule are the same thing. So I could call this u. I could say u equals 2 minus y. And then I could say du dy is -1. Right, and then dy then would be du over -1, and that -1 would come out. So this is kind of, remember I said when these are linear, we can do them quickly. We don't typically have to go through all the u sub steps. Okay, the right side, take a sigh of relief here. The right side is just a natural log of the absolute value of x, and then plus c. So here is our general solution. So notice I have to solve for y. Oops. And which means I have to get rid of the natural log. So this is where the exponentiation comes into play. And that was the example at the top of your notes where we said e to the natural log of y is y. But we'll get to that in just a second. Okay, so we want a particular solution. We have an initial condition. We're going to put that initial condition in right away to get C. So we're going to go ahead. Y is equal to 1, x is equal to 3. So I put a 1 in here for y. I put a 3 in here for x. And I solve. Okay, so 2 minus 1 is 1. So we have natural log of 1 over negative 1 equals natural log of 3 plus c. Natural log of 1, that's one of those important things to know. This whole thing is 0. So we have 0 equals natural log of c, or 0 equals natural log of 3 plus c. There we go. Taking that to the other side, c is negative natural log of 3. So I'm going to put this in to my general solution right here. So it's going to look like this. Minus, I'm just going to call it minus up front here, minus natural log of 2 minus y equals natural log of x minus natural log of 3. Now you may notice that I dropped the absolute values as well. Okay, and at this point in the solution, that is okay. And I'll show you why in just a little bit. Well, I can show you why now, because we're concerned about this. And we're concerned about this initial condition, and we know that when we put in the y here, we're going to get a positive value, and when we put in an x here, it'll be a positive value. So we can drop the absolute values. Okay, so I've got to solve for y, and I've got this minus sign on the outside, so I am going to multiply through by negative 1 to get the minus sign out from the natural log where my y is. So that's going to make this positive, this negative, and this positive. Okay, so I'm going to start a new screen here. All right, so the first thing we're going to do here is we're going to leave this alone, but this is, remember this property from the beginning of the video, right? I have ln3 minus lnx. Wherever the minus sign is, that's the thing that goes in the denominator. So this is ln3 over x. Now, this is the cool thing about this particular problem. We have an ln on the left and an ln on the right. And so if you remember how to get rid of that natural log, you exponentiate. But in doing so, really, you just get this, 2 minus y, because these will be in the powers, or equals 3 over x. So when we have the ln on the left and the right, we can just drop them. And so I'm just going to backspace here because this is important. That goes back to this arrangement, right? When we separated this and we saw y in the bottom and x in the bottom, it's going to be an ln sort of scenario. And when we have an ln scenario, we're going to just end up dropping the ln's anyway, as soon as we've rewritten it to be ln of something equals ln of something. So kind of, if you can see those things up front, that helps out. Okay, so now solving for y is no big deal. I can just add y to both sides, subtract this from both sides, and here's solving for y. So there is my particular solution. Okay, so now I'm going to put a qualifier in here. This goes back to a couple of things. One, we want to keep x positive because we do actually need an absolute value, right? Because of the natural logs that appeared in the solution. We also don't want it to be 0 because of this rational expression. So here's a qualifier. Now, a little tidbit of information. If they are asking you for the particular solution and you don't have this, I haven't run into a situation where they docked you any points. So this is kind of just a good to know thing. Okay, so let's take a look at this question. It's a little bit different. Right now there's an x squared on the bottom. Okay, but there's still a y minus, in this case, y minus 1 instead of 2 minus y, but there's still that same sort of term on the top, same sort of linear term on the top. Okay, so let's go ahead and separate our variables. Multiply by dx, divide by y minus 1, or multiply by its reciprocal, get those to cancel. So we end up with that after they're separated. So let's take a look at this. First thing, we still have a 1 over something to the first power, something linear, right? So we know this left-hand side is going to be a natural log. The right-hand side is 1 over x squared, which is x to the minus 2. This is not going to be a natural log because of the power on the x. So we're not going to have the natural log thing anymore. Okay, they're not going to cancel out. So this is definitely a natural log. There's no way around it. We're definitely going to have to deal with that natural log. We won't be able just to cancel it out like the last example. Last example, I think this said like natural log or maybe not, right? And it wasn't. We ended up being able to cancel out. This time we can't cancel it. All right, so let's do the antiderivative of both sides. So we know this one is going to be the natural log of y minus 1. Now, we don't need the u sub on this one because the derivative of this is 1. It would be like dividing by 1, which is irrelevant. So this is just a straight natural log. Remember, the other example had the y over here with the negative sign. So that's why we ended up having that u sub and having to divide by the negative 1, because that's what the derivative was. Okay, so this side, let's bump up the power, divide by the new power. So x to the minus 1 over minus 1, and then plus RC. Okay, so let's clean this up a little bit. I think that's what I do in this next step here. So we have natural log of the absolute value of y minus 1, and we're going to call this minus 1 over x plus c. So there's our general solution. Let's get our c. We've got to do that right away. So here's our initial condition. When x is 2, y is 0. So we're going to put 0 in for y. This is where the absolute values are absolutely important, because we can do that and we can still evaluate this. And then we're going to put in 2 in for x. Okay, so this is the natural log of the absolute value of negative 1. That means the natural log of 1. And the natural log of 1 is, go back to your important values, natural log of 1 is 0. So the natural log of the absolute value of negative 1 is 0. So now we know that we have 0 equals negative a half plus c, or c equals a half. So now I'm going to come back to this general solution and write y minus 1 equals minus 1 over x plus a half. Put in that plus a half for c. Okay, so now I got to solve for y, because I need the particular solution. And the particular solution involves solving for y. Right? That's why they say this, y equals f of x. Find the particular solution, y equals f of x. That is telling you to solve for y. So in order to solve for y and get the natural log out of there, we need to exponentiate. So this goes back to algebra 2. So exponentiating involves taking each one of these and calling them the power of an exponential function. So it looks like this, right? E to the natural log y minus 1 equals e to the all of this stuff, right? And so that's why I need the brackets. All of that becomes the power. This, okay, and this is the reason why we do this. This gets rid of the natural log on the left. So this is just the absolute value of y minus 1. Okay. This we're going to rewrite. Remember the must knows at the beginning of the video, right? E to the x plus y is e to the x times e to the y. That's where we need this skill here. This is e to the minus 1 over x times e to the half. And I'll do that in the next step. Okay, so I'm going to drop these absolute values. I'll tell you about that in a second. I'm going to rewrite this as, well, I guess I didn't rewrite it yet. Gosh. Well, I'm going to eventually rewrite this. Okay, I'm going to drop these absolute values because what I'm going to say is this, kind of going back to the natural log of negative 1, right? The stuff inside can either be positive or negative. So when we drop the absolute values, we say we have a decision to make here. Should this be positive or should this be negative? So we put a plus or a minus over here. And then we can add 1 to both sides. Okay, well, I don't know why I'm not separating these, but I guess, technically you don't have to solve for y. You can keep them together like this. Sometimes it's advantageous to separate these. I think I might have an example for that. Okay, so now we have to decide which one do we keep. And it goes back to this initial condition. This initial condition has to work in whatever you write down here. So when x is equal to 2, I better get 0. So if I put 2 here, then it makes the power 0. E to the 0 is 1. So I must need the minus sign so that 1 minus 1 gives me 0. If I use the plus sign, I will get 2. So I have to pick, since because of this initial condition, I have to pick the minus sign as my particular solution. think about this. This is two different functions. 1 plus e to the minus 1 over x plus half, and 1 minus e to the minus 1 over x plus half. So those are two different functions. I have to pick the right function that will match my initial condition. So here is my particular solution. Okay. Let's navigate a multiple choice question. So here's my differential equation. And it's saying for y greater than 2, that's because we're going to run into a natural log situation, and we want to make sure we have a positive there so we can drop the absolute value signs. And I'll show you that as we go through this. And then we have this initial condition, y to the 4 equals 5. Now, multiple choice questions are always nice because if you're savvy, kind of like in the last unit with our inverse trig functions, sometimes you can find the answer before you get through all of the steps. So we're going to try that, try applying that skill here. All right. So in other words, can we see the answer before we're done? Okay, so I know it's hard to read here, but I'm going to try to multiply. I'm going to multiply by dx. I'm going to try to do this all up here. And then I need to move the y. So I'm going to divide by y minus 2. And it's going to cancel out on the right. And so if you can see everything up here, I've got 1 over y minus 2 dy equals x minus 2 dx. So there's my separation, my separation step. And then I'm going to anti-differentiate both sides. So first glance at this, we know this is going to be a natural log, and we know this is not going to be a natural log. So just like the previous example, we're going to have e to something. So that being the case, this is a natural log antiderivative. This is a polynomial antiderivative. It's going to be just like the last example. I mean, if you remember, that last example ended up being something that kind of looked like this, right? An e to a power. So we can rule out c and d. We know we're going to have to exponentiate somewhere in this solution. So we've already eliminated half the answers. That's pretty cool. All right, let's see what the next step gets us. Okay. Well, think about this. This is going to be the natural log of y minus 2. And after we exponentiate, if you think back to the last example, after we exponentiate, we're going to have y minus 2. So what we're going to end up having to do eventually is bring the 2 to the other side. Which one has a 2 on the other side? This answer has got to be B. So just in the separation step, if we can kind of look ahead without going through the steps, we can usually narrow down the answer on these type of questions, which is kind of cool. It's a big time saving. All right, so if you want to see the steps, go ahead and keep tuning in. If you don't, you can fast forward to the last example. Okay, so I'm going to go ahead, natural log of y minus 2, anti-differentiate that, x squared over 2 minus 2x plus c. I'm going to use my initial condition of 4, 5. So I'm going to put a 5 here. I'm going to put 4s here. Why did I put 0s there? That's not good. Should have put 4s there. Let me change that. Interesting. Okay, let's put 4s there. 4 there. So what do we have here? We got 16 divided 2, which is 8. Minus 8. Oh, 8 minus 8 is 0. Wow, that's kind of cool. So I did put in the wrong number there, but it ended up being 0 anyway. Let me catch up to my animation where I should be. So if you remember, I had 0s there. And so it would be 0 minus 0 equals c. Now I have 8 minus 8, which is still 0. So c is still natural log of 3. So even though I originally had the wrong numbers there, it ended up being the same answer. Okay, so we know c is natural log of 3. If you notice, this one has a 3 in it, so that should help you as well. So I have that. Okay, and so let's exponentiate both sides. It gets a little messy looking, but really it's just that. right? All I'm doing is putting brackets around this whole thing and calling it an exponent. That's all I'm doing. This is the left-hand side is just going to be y minus 2. This is where I'm going to do that thing I mentioned in the last example. I'm going to separate this. I'm going to take everything that has a variable and keep it together as an exponent. And then I'm going to go times e to the natural log of 3. Because e to the natural log of 3 is kind of like e to the natural log of y minus 2. If this is just y minus 2, then this whole thing is just 3. And then I'm going to bring the 3 out front. Okay, so, and I also, at this point, when I drop the absolute value signs, I have my plus minus over here from the discussion from the last example. And so now you can really see what the appropriate solution is. And when I add 2 to both sides, I get exactly what I see in B. Okay, so that was a lot of steps. So if you can start to see the answer after the first couple of steps, that's just a monumental time saver. That's why I really highly encourage that on multiple choice questions. Okay, so according to the initial condition here, I want, when x is equal to 4, I want y equal to 5. And the only way to get that is to take 2 and add something to it. So I must need the plus option, not the negative option. Okay, so here's a motion application. But even though it's a motion application, the process is still the same. We're going to still find that particular solution. Okay. And so here is my differential equation. And so I'm going to multiply both sides by dt, and I have to divide out this whole thing because, again, I don't have a product here. I have a difference of 2 terms. So this is the cool thing. They will give you this from time to time, but you will always be able to factor something out and make it into a product. So that's the cool thing. So that's what we're going to think of it is we're going to, and then I have a typo here. Gosh darn it. I don't think I've ever had so many mistakes. This should be 2 times the quantity. In fact, the negative 2 shouldn't even be there. It should be v plus 16. There we go. Hold on here. Darn it. There we go. V plus 16. There we go. Sorry about that. Okay, let me catch up. There we go. So, so if this is 2 times the quantity v plus 16, then I can divide by v plus 16, and I can multiply each side by dt, and the negative 2 just stays on the right-hand side. And then I can do the antiderivative of both sides. Okay, so looking at this again, remember that the focus here is logarithmic and exponential scenarios. This is going to be the natural log of v plus 16. This is going to be 2t, negative 2t, excuse me, plus c. I'm going to exponentiate, excuse me, I'm not going to exponentiate, I'm going to fill in the initial condition. So when v is equal to negative 50, t is equal to 0. So c is the natural log of negative 30, absolute value of negative 34, which is just the natural log of 34. So I'm going to put that in for c. So the particular solution here is natural log of v plus 16 minus 2t plus natural log of 34. And then I'm going to exponentiate both sides. I could have put brackets here too. That probably would have been a good idea. And then we know that this e to the natural log of v plus 16 is just v plus 16. I still have my absolute values there. And this I'm going to rewrite as e to the negative 2t times e to the natural log of 34. Anytime you can do this with a numeric expression, we know that it's just the number. So the 34 is going to come out in front here. I'm going to drop these absolute values in a second. There we go. I'm going to put my plus or minus here. I'm going to bring my 34 in front. And then I'm going to subtract 16 from both sides. And then I'm going to select the negative answer because of my initial condition. My initial condition is that when t is equal to 0, my velocity is 50 downwards, right? Negative 50. So it means 50 feet per second downwards. That's a skydiver, so they're moving down. So in order to get negative 50, I'm going to have to take negative 16 and subtract something, right? Subtract 34. So I need the negative option for my particular solution. So here is my particular solution. Okay, so when we get back into the classroom, we'll go over the takeaways and we'll work on our focus on logarithmic and exponential applications of differential equations.